Welcome back to the deep dive. Today, we are heading pretty far north, actually. We're going to unpack an academic analysis that tackles a huge question. Can a highly industrialized northern European country, Finland in this case, transition its entire energy system to 100% renewables? And crucially, can it achieve full energy independence and maybe even save money doing it?
It's a fascinating prospect.
Our source material today is, well, it's a bit of the deep dive into the future, or at least how people saw the future back then. It's an older paper, published back in 2016, but it was looking ahead to 2050. The full title is Vision and Initial Feasibility Analysis of a Recarbonized Finnish Energy System.
Right. And it gives us this really interesting snapshot of how experts were thinking about radical system change almost a decade ago. So our mission today really is to pull out the key findings. What did they see as the technical pathways, the economic pathways for Finland? The researchers used this method, an initial feasibility analysis. They actually called it an overnight study. The idea was to investigate this whole transition case, just in principle, for the year 2050. Could the system actually work purely on domestic resources?
Okay, and the big finding, the headline result that really must have turned some heads back in 2016.
Well, the main conclusion was pretty stark. A 100% renewable energy system. It's not just technically possible for Finland, even with its northern climate, but it was also the lowest cost option. Out of all the future scenarios they modeled, renewables came out cheapest.
Lowest cost. Okay, that definitely grabs your attention.
Yeah, and what's really interesting is how thorough this study was. They weren't just, looking at the electricity grid in isolation. No, they modeled a fully integrated energy system. So
Yeah.
power, heating, cooling, even mobility cars, transport. And they calculated everything on an hourly basis using this pretty sophisticated tool called Energy Plan.
Hourly. Wow.
Yeah, and that integration, that linking of sectors, that's really the key to getting the flexibility you need in a system like this.
Okay, let's unpack this cost thing. You said lowest cost. Can we put some numbers on that? How cheap are we talking compared to, say, sticking with the status quo or maybe using more nuclear?
Right. Let's look at the figures. The study's sort of best case 100% RE scenario that had an estimated overall annual cost for Finland in 2050, about 24.1 billion euros per year. Let's call it BM.
24.1 billion euros. Okay, that's our baseline.
Now compare that. The scenarios where they included higher shares of nuclear power, the cost went up. They rose as high as 26.4 billion euros per year. And if you looked at the reference case, the business as usual or BAU scenario, which still relies heavily on fossil fuels, that was also generally more expensive than the 100% renewables option.
Right, so the gap between the top nuclear option and the 100% RE is what? About 2.3 billion euros difference every single year?
Yeah, roughly that, which is, not insignificant for a national budget.
Definitely not.
But if you look at the bigger picture here, it's maybe less about the specific number, 24 versus 26 billion, and more about this fundamental shift in where the costs come from and the risk.
Okay, tell me more about that cost shift.
Well, think about the BAU scenario. The costs there are dominated by variable stuff, mostly paying for imported fossil fuels and paying for CO2 emissions. This leaves Finland really exposed to, global market swings, geopolitical issues, carbon price volatility, huge risk.
Right, things outside their control.
Exactly. Now, the 100% RE scenarios, they completely flip that risk profile. The costs become dominated by fixed things. Paying off the investment in the infrastructure like wind turbines and solar panels and predictable operational costs. And crucially, it relies only on domestic resources, sun, wind, biomass, things Finland has.
So more predictable costs, less external risk. And the study actually quantified that risk exposure, didn't it? Especially around carbon pricing.
Oh, absolutely. It was quite clear. They calculated that the BAU scenario's annual costs would jump by about 250 million euros, just for every 10 euro per ton increase in the carbon price once you go above the 75 euros per ton they assumed in the base analysis.
Wow, 250 million extra cost for every 10 euro jump in CO2 price.
Yeah, whereas the 100% RE scenarios, they're just not sensitive to that risk at all. That stability, that insulation from carbon price shocks, that might actually be the single biggest economic argument for going 100% renewable beyond just the raw annual cost figure.
Okay, the economics seem pretty compelling, especially on the risk front. But let's tackle the elephant in the room. Finland. High latitude. We're talking long, dark winters, not exactly known for endless sunshine. I mean, intuitively, you'd think solar power would be, well, difficult, or at least not very efficient up there.
Right.
How on earth did this study make solar work? especially storing summer sun for the dead of winter.
Yeah, it seems counterintuitive, doesn't it?
Yeah.
But the technical finding was actually quite surprising. They found high shares of solar PV photovoltaics were completely feasible.
Feasible. How high are we talking?
We're talking significant capacity, 30 gigawatts. That's gigawatts peak, the maximum output in the basic scenarios. And it went up to 35 gigawatts in some scenarios where they used less biomass. That's a lot of solar panels for a northern country.
Okay, 30 to 35 gigawatts peak. But how? How is that possible when you have months with very little sunlight?
Well, the key isn't relying on the sun shining right now. The key is system flexibility and critically seasonal storage. You generate when you can and you store it or convert it for later.
Convert.
Exactly. So the solar PV and the wind generation, they're supported by this whole network of energy storage solutions. And they're also balanced out seasonally by generation you can control, like from biomass or stored fuels.
Okay, so storage is key. Let's dig into that. You mentioned converting energy.
Hmm.
What kind of technologies are we talking about? We hear terms like power to X.
Right. Power to X is central here. Think of it as the engine for energy independence, especially for seasonal storage. The two really critical conversion technologies they modeled were power to gas, or PTG, and power to liquid, PTL.
Power to gas and power to liquid. Okay.
So these are industrial processes that take surplus electricity, maybe from those huge solar farms on long summer days when demand is lower to Blake's, and they use it to create synthetic fuels. PTG makes synthetic methane, basically renewable natural gas. PTL makes synthetic liquid fuels like diesel or kerosene.
Ah, so you turn electricity into a fuel you can store.
Precisely. You can store these synthetic fuels pretty much indefinitely in tanks or gas networks, and then use them later for heating in winter or maybe for trucks or planes. And the scale they envisioned was massive. The model included up to 15 GW capacity just for the power-to-gas sector.
15 GWh, what's the E's stand for there?
Ah, good question. GWin is gigawatts electrical. It refers to the amount of electricity that conversion plants consume when they're running. So 15 gigawatt of power needed just to make the synthetic gas. It shows how significant this conversion process is.
Okay, huge conversion capacity for seasonal storage using synthetic fuels. What about more direct storage, like batteries?
Yep, they included batteries too, both stationary ones and, interestingly, mobile ones in cars. For stationary batteries, the model had about 20 gigawatt capacity.
GWH, so gigawatt hours, that's the amount of energy stored, right?
Exactly. 20 gigawatt is the total energy those fixed batteries could hold and deliver over time. But maybe the most flexible asset in the whole system, according to this model, was V2G, vehicle to grid.
Vehicle to grid, right? Where electric cars basically act as batteries on wheels for the grid. How big a deal was that in the model?
A huge deal. They assumed 3 million battery electric vehicles on finished roads by 2050. Collectively, that's an enormous potential storage capacity, something like 300 gigawatt hours total, just in car batteries.
300 gigawatt hours. Wow, that dwarfs the stationary batteries.
It really does, and the study made a fairly conservative assumption that maybe half of that total car battery capacity would be available for V2G services at any given time. So you essentially turn millions of parked cars into this giant distributed flexible energy reservoir. It helps buffer the grid against short-term ups and downs in wind and solar.
That's a really comprehensive picture of flexibility, synthetic fuels, big batteries, and using all those EVs. Okay, let's shift gears a bit. The study also looked at how nuclear power and biomass affect the costs in these future scenarios. Let's start with nuclear. What did they find?
Well, the results there were pretty clear-cut in this analysis. They found that the total annual cost of the energy system across all the scenarios they tested was directly related to how much nuclear capacity was installed. Basically, more nuclear meant higher total system costs.
Higher costs with more nuclear. Why was that?
It really came down to the assumptions they used for new nuclear plants by 2050. They assumed a cost of 6,500 euros per kilowatt electric. Kilo. And importantly, they based this on what they called a negative learning rate.
Negative learning rate. That sounds counterintuitive. Usually technology gets cheaper over time.
Right. But their argument, based on historical trends for large, complex nuclear projects at the time, was that capital costs for nuclear had actually been increasing, maybe due to rising safety standards, supply chain issues, project complexities.
That's a pretty bold assumption, especially looking at today's talk about small modular reactors, SMRs, which aim to cut costs. Did they address that potential?
Not explicitly SMRs, as this was 2016 thinking mainly about large reactors. Their justification was rooted in the observed costs of large projects built over previous decades. And beyond just cost, They also pointed out that nuclear power is one of the least flexible parts of an energy system.
Less flexible. How so?
Well, nuclear plants like to run constantly, providing baseload power. But in a system dominated by cheap, variable renewables like wind and solar, what you actually need is flexibility to match supply and demand, not just constant baseload. The study suggested very little baseload power would be needed in this future Finnish system. So nuclear's inflexibility became a drawback.
Okay, so higher assumed capital costs and inflexibility worked against nuclear in this model. And they also looked at emissions, right? Life cycle emissions.
Yes, that was another point they highlighted. When looking at the entire life cycle construction, fuel, operation, decommissioning, they cited figures showing nuclear power having significantly higher GHG emissions. Around 66 grams of CO2 equivalent per kilowatt-hour of electric, GCO2 keyword.
66 grams. How does that compare to renewables?
Well, the figures they used for wind energy were much lower, around 9 GCO2 keyway, and for solar PV, about 32 GCO2 keyway.
So quite a difference, especially if your goal is getting as close to zero emissions as possible.
Exactly. It factors into the overall picture when decarbonization is the primary goal.
Okay, let's switch to biomass then. Finland's a heavily forested country, so biomass must play a big role. How did that factor in?
It did, and it was a really interesting comparison. They looked at two main levels of biomass use. One scenario used what they defined as the maximum sustainable level of biomass, mostly forestry residues, which came out to 145 two-way per year.
Two-way. That's terawatt-hour thermal, right? Measuring the heat energy.
Correct. It's the total energy content from the biomass, used mainly for heating and some combined heat and power. So 145.2 was the high biomass case. Then they compared it to a low biomass scenario, using only 113 two-way.
And the cost difference.
The maximum sustainable use scenario, the 145 two-way one, actually resulted in the lowest overall system costs.
So using more biomass was cheaper.
In their model, yes. Biomass provides dispatchable heat and power, which is valuable for balancing the variable renewables. It fills the gaps effectively. In fact, the scenarios that restricted biomass use, the low biomass ones, saw costs increase quite a bit. So much so that in some low biomass cases, the fossil fuel BAU scenario almost looked competitive again on cost energy, which is obviously not the direction you want to go if you're aiming for decarbonization.
Wow, okay, so restricting biomass made things tricky. But was the 100% RE low biomass option still viable?
Oh yes. Even the 100% RE low biomass option was generally still cheaper than the fossil or nuclear-heavy scenarios. It just wasn't as cheap as the 100% RE max biomass option.
How big was that cost difference between the two 100% RE biomass options?
Actually not huge. It was about €500 million per year, 0.5 BO between the ABS biomass and low biomass 100% RE scenarios.
Only $500 million. That's interesting.
It is, because it raises this really important question that goes beyond just the energy system economics. If using less forest biomass only costs slightly more, could there be other non-energy benefits that make it worthwhile?
Like what?
Well, maybe leaving more forest standing could enhance natural carbon sinks, absorbing more CO2. Or perhaps it supports biodiversity or boosts industries like ecotourism. So the question becomes, are those wider environmental or social benefits worth that extra €500 million in energy system costs?
That really frames the final decision point, doesn't it? It's not just about the cheapest electrons. So the study basically lays out two main zero-emission paths for Finland by 2050. Path 1, 100% renewables, using the maximum sustainable amount of biomass, lowest cost in the model. Path 2, 100% renewables, but deliberately using less biomass, accepting a slightly higher energy cost for potential wider benefits.
Exactly. Both paths get you to essentially zero greenhouse gas emissions from the energy sector itself. And this is where the conversation really has to shift from pure engineering and economics towards, societal values. What kind of future do people want? The study itself touches on this, especially when discussing nuclear again in the broader context. It brings up those wider sustainability issues like the ethical problem of nuclear waste that lasts for generations.
The intergenerational equity issue.
Yeah. And they also cite research current at the time about the risk of major accidents. They mentioned one assessment suggesting a 50% chance globally of a Chernobyl-scale event every 60 to 150 years.
That's a sobering statistic.
It is. And they also note that nuclear sites, even after decommissioning, remain permanently altered environments. These are societal costs, hard to capture fully in just euros and cents.
But looking at the transition itself, the timing, did the study suggest a need for a crash program shutting down existing plants early?
Actually, no. One interesting point was that the transition away from fossil fuels by 2050 could likely happen without forcing the early retirement of existing fossil fuel power plants. Their average operational lifetime seemed to roughly align with that 2050 timeframe anyway.
So it's less about demolition and more about direction.
Exactly. The critical thing is the decisions about future investments. Where does the new money go? Into renewables and flexibility, or into extending the life of the old system, or into options like new nuclear with those cost and risk profiles we discussed. It's a crossroads.
A real crossroads.
And I think what really stands out from this study, looking back, is that the final choice isn't just a technical or economic calculation. The public discourse needs to include these deeper questions. How do we as a society perceive risk? What does energy security truly mean to us? What's our relationship with our natural resources like forests? Because the cheapest option on paper isn't automatically the best option if it brings other risks or conflicts with how people want to live.
That's a powerful point. It's about values as much as volts and euros. Okay, let's try to quickly sum up the core insights from this deep dive into Finland's possible energy future as seen back in 2016.
Sounds good.
First, the really big one, the potential cost competitiveness of a 100% renewable energy system. It challenged the old idea that going green has to be more expensive.
Absolutely. Second, the surprising technical feasibility of using lots of solar power even in the far north. It can be done.
But only because of the third insight, right? The absolutely vital role of massive system flexibility.
That's the key. Harnessing storage batteries, V2G, and those power-to-X processes like power-to-gas and power-to-liquid to handle the variability, especially between seasons.
And finally, the study's analysis suggested that nuclear energy, due to its assumed rising costs back then, inflexibility and other risks, wasn't the most attractive option for this particular vision of a low-cost domestic renewable future.
Right. The overall conclusion from this specific analysis was pretty clear. Future energy planning in Finland should really center on that vision of 100% renewable energy. It shifts the focus from managing external risks, like fuel prices, to maximizing Finland's own domestic resources and benefits.
A really thorough investigation. This was our deep dive into the findings of vision and initial feasibility analysis of a recarbonized Finnish energy system.
A mouthful, but an important study.
Indeed. And maybe one final thought for you, our listener, to chew on. Given that this study showed the 100% RE scenarios having the least exposure to long-term financial risks, things like volatile carbon prices or maybe unexpected cost hikes for complex technologies, should that risk exposure itself become the primary way we define long-term energy security? Maybe even more important than the initial sticker price.
Something to think about.
Definitely. Until next time, keep digging deeper.